Now, Mariano Vazquez, who is also to be sort of confirmed as one of the members of our scientific advisory board, and he's going to talk further about the biomedical sector.
Okay. Well, thanks a lot for inviting me here. And well, in my talk, you are going to see some plenty of conceptual things that have been said in the two previous talks. So even if it is in a different level, but there are plenty of things that are common. So first of all, I would like to ask, our center is not directly involved in the project. Then I will give you in a couple of slides what is our center. Well, if you go to Barcelona, you see all these churches there, cathedrals, whatever, like in a typical European city. So this church here, this chapel, is not very famous because, well, it's not at all, except for the fact that inside this chapel there is this computer. So this is Mare Nostrum, is our baby. It's large computer. It's about 13 petaflops. But to us, what is interesting is that it is a 4-in-1 supercomputer. So there is one very large general purpose block, which is made of off-the-shelf components with these 11 petaflops with 165 processors. But then what is interesting is that we have also these, what we call emerging technologies, or technologies blocks. So the second one, you can forget about the second one because Intel is going to decommission this KNH. However, it's still there. We are on the way of Fujitsu is on the way to providing us these 64-bit ARM processors. So it is being done right now, and we have started these Power 9 plus NVIDIA Voltage GPUs. It is right now working. We are using it, and it's very nice. It's a large, small computer because it is 1.5 petaflops. And I was just coming here. I was reading that it was selected as at the top European in the Green 500 computers. So it is very efficient due to the fact that this Power 9 combined with this NVIDIA GPUs is very efficient in producing flops per consumed power, which is something that is, of course, very important. So the BSc is a public research center, is divided in departments. We are kind of 500 researchers, and my department, I will talk about life science, but my department is the applications department, because life science is mostly devoted to bioinformatics and computational biochemistry, so I will talk about simulations of continuum mechanics simulations, tissue and organ level. So there is one department that is the applications department, because, well, it can be, and this is also slightly related to Professor Chantel said before, the role of computer science people in modern science. So in this case, we are, well, myself, I'm a physicist, but the department is kind of a computer science department. So we are fully devoted to writing code from the very beginning, from mathematical models to run efficiently in these very large supercomputers. So our department, we are more than 90 researchers, and we have postdoc students, programmers, designers. That's why you're going to see nice, some beautiful visualizations of the simulation. So they do not take them as cartoons. They are visualization of scientific results, but done with cartoon techniques. So, well, we are from different backgrounds. If you look at the research lines, they are kind of the typical research lines that you can find in a computational mechanics group, if this exists. So it's more or less, well, always kind of jargon that you can read in a web page of computational mechanics group. But what is interesting to me is the applications line. So it is like we are computer science people looking for a problem to solve. So it is not the other way around, which many times happens, that you are you work in something and you need, and you say, oh, I need a code, then you write a code. Oh, I need to be more efficient, then you make it more efficient. So in our case, it is kind of the other way around. So we write the code for complex multiphysics problems, and at the same time, let's say we are looking for, it's been kind of 12, 13 years that we are doing that, so it's not just right now. But it's like, as I said before, just people looking for a problem to solve. That's why we establish very nice collaborations. However, I have to say that in some of these fields, after working a lot with that, we start bringing scientists of this field on board that are working with us. And for instance, for aerospace or oil and gas, but also for in biomedical research. So after a while, we start having interest ourselves in doing biomedical research itself. So we have bioengineers that are working on board in the center. So we developed a code which is called Alya. This code is a multiphysics code. It's it was born about 12 years ago. Right now we have more than 40 researchers, kind of 50, in the center working in the code, and another 40 outside the SC working with it. Some of them are programmers, some of them are users, but I would say that most of us are programmers and users at the same time, like ourselves. And it is used in industry-related projects like aerospace, imaging, environment, and biomedical, which is the one I would like to talk about now. So the keywords of our code is that it is always, well, you see these complex geometries, physical, mathematical models, usually unconventional, kind of, well, difficult problems. Pre-process is difficult, post-process too, because the meshes are very large, so there are plenty of data that you have to analyze. And in general, we use it for large-scale simulations. But I have to say that what we are mostly focused in is in multiphysics problems. We would like to do multiphysics in the most efficient way for supercomputers. If we are solving two physics, one very, let's say, fluid-struct interaction, let us imagine that both of them are very expensive in computational terms because the structure has, let's say, wing and have plenty of composites and fracture and things like that. Then you can imagine now that you are using a very nice code or two different coupled codes. Then you cannot allow that you cannot allow yourself that the bottleneck is the coupling. Even from the algorithmic point of view, not just the programming. So what we do is we try to make this the most efficient as possible for the coupling. So just for fun, we put some colors to the things that we do using Alya. So we call Alya red. What is using is everything that where we are using Alya, and it is related to biomedical. So we work at organ and tissue level, that is to say at continuum mechanics hypothesis, although we need coupling from below and coupling from above, but it is at this point. In general, there are complex problems requiring supercomputers. Of course, we do very small things in order to validate or verify the code, and it is mainly focused on cardiovascular and the respiratory system. So what I will do now is I will just give you a glimpse of the kind of things that we do, focusing in two problems. And then, well, you can ask me for the technicalities of the problem, but, well, what I will do, just not to bore you, I will just show some examples of the things that we do. So for the cardiovascular, we work mostly into, let's say, in two domains, like cardiac and vascular. So the features are, it's multi-physics, it's computational fluid dynamics, solid mechanics, because we have fluid-struct interaction, electrophysiology. It is typically large-scale meshes, so we need to develop multiphysics, efficient multiphysics coupling algorithms. Again, the algorithm and also the way of programming it. You have contacts if you would like to study the deployment of the stent. Mesh generation issues, because this is typically geometries are coming from data, medical images. So mesh generation is an issue, and then data analytics and simulation. So, well, let's focus in the cardiac because it is the less familiar. probably to most of you. So if you think about the cardiac problem, it's you have some electrical propagation that it is propagating in the cardiac tissue that unleash this mechanical deformation, and this mechanical deformation of the ventricles atria is working against the blood flow. So the green problems are the coupling, so they are a problem in itself. The fluid mechanics fluid structure interaction problem is more a mathematical one. It's not that difficult. I mean, there are plenty of people that have, as we say in Spain, in Spanish, left their skin doing good algorithms for doing fluid structure interaction, so it's not that problematic. However, the coupling between the electrical propagation and the mechanical deformation is more a physiological model, so it is much more controversial, and there are plenty of different strategies for doing it. So in the code, we have different, electrical propagation is a diffusion equation with some nonlinear terms that can be very nasty and very time-consuming in computational terms. Mechanical deformations is large deformation of nonlinear material models, and fluid flow is incompressible flow. In this case, it's Newtonian, but can be non-Newtonian. So this is an example of the kind of things that we do. So this is a full heart. We are not considering the atria, so the atria is like solid but soft material, and what we are considering is the ventricles that are contracting. So you can see this in the middle. So this is colored by electrical activity. So electrical activity more or less starts at the inner walls of the ventricle. So it propagates in the heart, in the ventricles, and this makes that the ventricles contract. Contraction of the ventricles are pumping out the blood flow. So in this case, what we are just studying contraction of the ventricles. So there are two valves that are fully open, just letting the blood flow get out, and two valves that are fully closed, which are avoiding the blood of the ventricles to get back into the atria.
5 minutes.
Yeah, so this is no valves here. And this is a disease heart, the one here. This is a disease heart that was filled. First of all, sorry, because as I said before, if we are going to have very nice visualizations with, well, these two are not that nice, in the sense that, for instance, this is done with visit, this is done with paraview. I mean, the heart is the same, but here you see vectors as velocity, field. Here you see these kind of streamlines. But anyway, you are going to see the idea. The idea is that in this heart, this is hard because there is no starting electrophysiology inside this ventricle. So what we have done is we put there a pacemaker. So there is a pacemaker, and we just change the activation frequency in order to see if we can recover the cardiac function. There are some amazing pacemakers also that goes inside the heart. So about 3 years ago, a company called Medtronic started to sell these kind of pacemakers that goes inside the heart. So you see they are these kind of small cylinders that get pinned inside the ventricle, and they are activating the electrical field around them. So this company, Medtronic, they were interested in they are interested in see at what extent this small piece of metal inside your heart is disturbing the fluid flow around. At what point this fluid flow around is the stresses that are done upon the pacemaker can eventually separate it from the wall. So this kind of things. So in this case, what we are simulating. And finally, respiratory system. So this is typically is CFD large-scale meshes. Particle transport, this is very important for them because in the respiratory system what we would like to see is to study the deposition maps of the particles that get into the system. There is some fluid structure interaction, not in the problem that you're going to see now because we are working on that. Mesh generation again is an issue, and data analytics and simulation, I will come back later to that. So it's difficult to imagine if you didn't see it, it's difficult to imagine how complex is the respiratory system that is behind your nose. So through the mouth is relatively simple, it's like a tube. But behind the nose is it's very complex. So we have all these cavities there. This is an example of the simulation. So in this case, this is fluid mechanics, continuum mechanics, while solving at the same time particles. So we are injecting particles in the nose, and we are studying the deposition map of the particles all along the system. So this is a very nice example of what is of a multiphysics problem, because in order to make, or of the difficulty of a multiphysics problem, because in order to make the particles transport and deposition the most efficient as possible, we are not doing this in post-process. We are doing this at the same time that we run the simulation. This brings a problem, and the problem is the parallelization paradigm of the particles is not the same paradigm as the continuum mechanics. So we have to be very careful in order to not to produce very high load balance problems. And just to finish, this is very interesting, because in this case it's again through the nose, and it is an aerosol where the treatment comes not at the moment that you inhale, but at the moment that as you exhale. Because what you do is you inhale your particles and then you exhale, and at the moment that you exhale, the particles go to some places that they can't go in the inhalation process. So it goes to a part of the nose that is very close to the brain. So this is very interesting for delivering drug, some specific drug against some diseases that must go as fast as possible to the brain. So the goal of this is not that the drug goes into the lungs, but it remains in your head and goes close to the sinus here, very close, which is the closest point to the brain. So again, this is not a particle stored. This is continuum mechanics, fluid mechanics, transporting particles. So a couple of slides about this, and I'm done. About high performance computing and high performance data analytics. Now, I said that in what we do is we simulate continuum mechanics, fluid mechanics, with particles transport. So what we are doing here is we are dumping the results of we are tracking the particles and just keeping the data of the particles, not the fluid mechanics part. Let's say we forget about the pressure and velocity, because the trackers of the velocity are the particles. So just we keep the information of the particles. So what we are doing is we run our code in an HPC system. Then we have deployed Cassandra, which is it was named before Cassandra, which is a distributed database. It is deployed in a different system. For instance, Mare Nostrum is not at all good for databases. The operation, the director of the operations department will not let you deploy any database in Mare Nostrum. Don't touch my computer. Don't put your dirty database in my computer. So you need to do this in a different computer. So it's a different system. And then what and Alya is doing, Alya is running in parallel in several cores, and what it's doing is doing directly the inserts in the distributed database at the proper places. And then what you can do, well, you store everything, and then the user can make queries to the database. Queries like, such as, I would like to know these particles of these sizes that are deposited at these places where they were coming from. And what you can do is you can run many simulations of changing parameters of like physical condition, design of the inhaler, the way that this person is inhaling, and you can now ask the queries to exploring the full database, just taking this into account. And well, there are two more slides. So the fact is that how can we put all this potential in the hands of blah blah blah. So what we have done is this is something that we have done been working in the last year to do these virtual humans factories. So we took this concept then from Biomedical project. So in this case, this is kind of a front end of what we do. That is to say, we try to sell this to companies in the sense that this is based on our code Alya, so this is a virtual human simulation software. Now the fact is that this supercomputing power is deployed in the cloud, and it is accessed as a software as a service model. So with a very sophisticated user interface, that it is not done. We have to develop it, but it's going to have a very nice user interface for the environmental side. So this was interesting because it brought us to many problems that we never considered. In some of the slides before, we talk about the users, and we talk about if we are developers and users, then it is very easy because, well, you know, just you program, and how do I input data? You just change some lines of the code and change some parameters. But you can't do that with people that really needs this. So this brought a lot of problems and a lot of material for research. Like for instance, in the last talk we've seen about the use of containers for deploying the applications in the cloud. We work with Oracle people, and well, we are just working with them to do these things fast. So the company is about to start. Yeah, that's it. So thank you.
Thanks, Mariano. Any questions?